Welcome back to the Deep Dive. We're here again to unpack some really complex, interesting ideas.
And today we're diving into something pretty cutting edge. AI for robots. Specifically, these things called Vision Language Action Models, or VLAs.
Right, and we're looking at a paper that tries to get at one of the real sticking points in this area.
Yeah, it's all about how you take these, massive AI models, the big language and vision ones trained on seemingly everything.
The VLMs.
Exactly, the VLMs. How do you get them to actually control a physical robot? I mean, a robot needs speed, precision, real-time reactions.
And that's the core problem, isn't it? These VLMs are brilliant. They understand language, concepts, put the spoon in the bin, that kind of thing.
But they learned it all from static stuff, text, images, not from, continuously moving an arm.
They weren't designed for that constant stream of adjustments a robot needs.
And the paper really highlights this issue. When you try to adapt these powerful VLMs, maybe add new bits for controlling actions.
Like an action expert.
Right. You often end up messing with the VLM's original knowledge. The very thing that made it useful in the first place starts to degrade.
It's like teaching a history professor to be a race car driver, and suddenly they forget the dates of major wars.
Something like that. Plus, just getting them to learn this new skill can be incredibly slow. The training takes forever.
Okay, so that's our mission for this deep dive. We need to understand the paper's proposed fix. They call it knowledge insulation.
Yep. We're going to unpack what that means, how it supposedly works.
See the proof they offer, and figure out if this really is a big step forward for making robots that can, do stuff properly.
Back to your analogy, it's like finding a way for the professor to learn race car driving without forgetting history.
All right, let's maybe start with the basics of these VLAs first, just to be clear.
Sure. So VLAs, vision language action models, fundamentally, they take a big pre-trained vision language model.
Something like PalaGemma, maybe?
Yeah, exactly. Train on tons of web data, and they extend it. They add capabilities so it can look at what a robot sees, understand a command in language, maybe check the robot's own state.
And then decide what action the robot should take next.
Precisely. And the big hope, the promise, is that by starting with that huge pre-trained VLM,
you get all its general knowledge for free, basically. Semantic understanding, knowing what objects are, how the world works.
Right. So the robot could potentially understand instructions about things it's never seen in its specific robot training data. Very powerful if it works.
But as you said, previous attempts hit some major walls.
They really did. First off, these VLMs are huge. Billions, sometimes hundreds of billions of parameters. Running that fast enough for real-time robot control. Tricky.
And then there's a mismatch between how VLMs work and what robots need.
Exactly. VLMs think in discrete chunks tokens, like words or pieces of images.
But robot actions are often continuous, right? Like the exact angle for a joint or the precise speed and direction for the hand to move.
Yes. Smooth, continuous values. So you can't just have the VLM spit out a word for an action. You need something more.
Which is where people started adding these extra modules, the action experts you mentioned, using things like diffusion models or flow matching.
Correct. Modules designed specifically to generate those continuous action signals. But here's the kicker, the problem this paper focuses on.
Okay.
When you just tack on these new action experts, which start out knowing nothing, they're randomly initialized, and then you try to fine-tune the whole thing together.
The VLM backbone plus the new expert.
Yeah. The learning signals coming from that new, untrained expert are often noisy, unstable, and those signals flow back and interfere with the carefully learned knowledge inside the VLM backbone.
So the new training actually messes up the old, valuable knowledge.
It can, yeah. It degrades the pre-trained capabilities.
Yeah.
And as a side effect, this whole joint training process can be much, much slower than other methods.
The paper had that example, didn't it? The bust the spoon into the bin task.
Oh yeah, figure 2. It's a great illustration. You see one baseline model, it just ignores the command, maybe sees the spoon, but doesn't get the bus it part. It lacks the language understanding.
And another one.
Another one, using a diffusion approach, eventually manages it, but it's painfully slow, like comically slow for a real robot. You see the trade-off clearly.
Get the continuous control, but lose speed, or maybe lose the language smarts. Neither is ideal.
Which brings us directly to their proposed solution. Knowledge insulation.
Okay, I'm ready. How does this insulation actually work? What are they doing differently?
So the core idea, and they show this nicely in Figure 1, is about setting up the training more cleverly. You control how information, and crucially, how learning signals or gradients, flow through the model.
Controlling the flow. Okay.
You still have your main VLM backbone initialized from a pre-trained model, and you still add a separate, usually smaller, action expert module for the continuous actions. They use flow matching in the paper, like one of the baselines.
Right. The Scholar backbone and the forklift driver expert module.
Hey, yeah. Now, here's the key difference. They don't just rely on the continuous action signal from the expert to train the VLM backbone. That's the signal that can be noisy.
So what do they use to train the backbone?
They train the backbone using something it's already good at, predicting sequences of tokens, like a standard language model task.
Tokens, but the actions are continuous.
Uh-huh. They convert the robot's continuous action trajectory into a sequence of discrete tokens. They use a method called the fast tokenizer, which basically learns a vocabulary for representing movements as tokens.
Okay, so they turn the robot's movement into a kind of movement language and train the backbone to predict the next word in that language.
That's a great way to put it. It gives the backbone a stable, familiar type of learning signal. It can adapt its internal understanding for robotics using a process it already knows well.
And meanwhile, what's happening with the action expert, the one doing the continuous stuff?
That's trained simultaneously, but using its own loss function, the continuous action loss, like flow matching. This teaches it how to generate those smooth, precise movements.
So two training processes happening at once. One discrete for the backbone.
And one continuous for the expert. But how do you stop the potentially messy learning from the expert spilling over and corrupting the backbone?
This must be the insulation part.
Exactly. The stop gradient. This is the crucial step. They computationally prevent the gradient, the error signal calculated from the action expert's continuous loss from flowing back into the VLM backbone.
Whoa. Okay, so the expert learns based on what the backbone tells it.
Right. It gets information from the backbone's representations.
But the expert's own learning process, its mistakes and adjustments, don't feed back to change the backbone's weight.
Precisely. The learning signal from the expert stops dead before it reaches the backbone. Information flows one way for prediction, backbone to expert, but the gradient for the expert's learning doesn't flow back up.
How do they actually implement that?
The paper mentions modifying the attention mechanisms like the communication pathways within the model. Equations 5 and 6 show how they control that information flow, essentially blocking that specific gradient path.
Got it. So the outcome you're aiming for is the backbone adapts using a stable token-based signal, keeping its general knowledge safe,
while the expert learns the specific, fast, continuous actions, informed by the backbone but not messing it up.
It sounds very elegant. Does the paper lay out a specific recipe for doing this?
It does, yeah. Section 5 details their training recipe, which has a few key ingredients.
Let's hear it. What's in the mix?
Okay, first is what we just discussed. The joint discrete continuous action prediction. Training the backbone on predicting action tokens, using that fast tokenizer, and simultaneously training the action expert on predicting continuous actions, using flow matching.
Right, the dual output, dual training signal thing.
Exactly. Second, and this is really important for keeping the VLM smart, is co-training with VLM data. Meaning they don't just train the model on robot task demonstrations, they mix that robot data with a bunch of general vision language data, think image captioning, visual question answering, stuff scraped from the web that the original VLM was likely trained on.
So you're constantly giving the VLM backbone a refresher on its original skills, kind of reminding it what language means, what objects are in general.
Precisely. It helps maintain that broad knowledge base and prevents it from forgetting everything it knew before robot training. It's key for generalization and language understanding.
Makes sense. Keep the scholar reading books while learning to drive the forklift.
Good analogy. And the third ingredient is, of course, the gradient flow. Control the knowledge insulation itself, implemented using that stop gradient we talked about, blocking the expert's noisy signal from reaching the backbone.
Okay. Joint prediction, co-training with general data, and the stop gradient insulation. That's the recipe.
That's the core recipe they propose.
It sounds plausible, definitely addresses the problems they laid out, but, the real test is, does it actually work better? Did they run experiments?
Oh, absolutely. They really put it through its paces. The paper has extensive experiments across a whole range of tasks. We're talking tabletop stuff like bussing dishes, folding shirts, but also more complex things like manipulating items inside drawers, including in environments the robot had never seen before during training, and even mobile manipulation tasks where the robot has to move around. Figure 3 gives you a good sense of the variety: real robots, simulations, standard benchmarks.
So a pretty thorough evaluation. And what was the verdict? Did the insulation method come out on top?
Yes, pretty convincingly. The results showed their method consistently outperforming the baseline approaches, especially on the harder tasks.
Like the drawer tasks?
Yeah, figure 4A is striking. On that items and drawer task, particularly in new environments, the baselines really struggle. Some just can't seem to open the drawer reliably. Their insulated method does much better.
And other tasks.
Similar story. Figure 5 shows it winning on table bussing. Figure 9 on the mobile manipulation tasks. They also hit state-of-the-art performance on some well-known benchmark suites, Libero 90 and Libero Spatial, which Table 1 details.
Okay, so better task success rates? That's obviously good. But did they prove the insulation itself was the key? That stopping the gradient was the magic ingredient?
They did a direct comparison for that. Figure 4B is crucial here. It compares their full method with the stop gradient against a version where they do the joint training but without stopping the gradient.
So letting the expert's learning signal flow back to the backbone.
Exactly. And the result is clear. Stopping the gradient significantly boosts the robot's ability to follow the language instructions correctly. It directly supports the idea that insulation protects the VLM's language understanding from getting corrupted.
That's pretty strong evidence for their core claim. What about just not training the backbone at all? Just freezing it?
They tested that too, and it performs poorly. Figures 4A and 8 show that freezing the backbone completely doesn't work well.
So you do need the backbone to adapt somewhat to the robot tasks. You can't just use it straight out of the box.
Right. Some adaptation is necessary for best performance. The VLM needs to learn how its general knowledge applies to these specific physical tasks, but the way it adapts is critical. Insulation seems to be the key to adapting it safely.
And you mentioned language following improved a lot.
Yeah.
Why is that specific aspect so important?
Well, think about it. If you want a general-purpose robot assistant, it needs to understand what you're asking it to do, right? Not just react vaguely to objects it sees.
You want it to put the red block in the blue bin, not just shove any block anywhere.
Exactly. And several figures 4B, 6A, 5, 7 show their method leads to better adherence to the specific language commands. The robot is actually listening, not just guessing based on vision.
And the co-training with general web data helps there too.
Yes, figure 6A suggests that mixing in that general VLM data further strengthens the language following ability. It reinforces that foundational understanding.
Okay, so better performance, better language following, proof that insulation works. What about the training speed issue they mentioned earlier? Did this approach solve that?
This is another big win they highlight. Remember how some previous continuous action methods, like pure diffusion across the whole model, were really slow to train?
Yeah, the agonizingly slow spoon busing.
Right. Well, figure 6B shows their insulated method trains much, much faster than those approaches. In fact, it trains about as quickly as the fastest autoregressive baselines, the ones that predict action tokens but might struggle with continuous precision.
So they kind of get the best of both worlds. The precision of continuous actions without the massive training time penalty.
That seems to be the case, yeah. They overcome that speed bottleneck.
Impressive. And what about generalization? You mentioned unseen environments. Does it also handle, say, objects it hasn't been explicitly trained on during the robot phase?
That's where the co-training aspect really shines. Figure 7 looks at what they call OOD follow rate, out of distribution. How well does it follow commands about objects it only saw in the general web data, not in the robot demonstrations? Including that general VLM data during co-training significantly improves its ability to handle those novel objects. It shows that protected VLM knowledge is genuinely helping the robot generalize its skills.
So it can connect, oh, I know what a widget is from the internet data to now I need to pick up this specific widget in front of me.
That's the idea. Leverage that vast world knowledge. They also found some smaller interesting things, like using that specific fast tokenizer was better than simpler discretization, figure 5. And the whole approach worked whether the robot's state was fed in as text or continuous numbers, figure 10.
Okay. Stepping back then, this does feel significant. Why is nailing this knowledge insulation idea so important for the future of robotics, would you say?
Well, I think it offers a really practical way forward. We have these incredibly powerful foundation models, VLMs, trained on staggering amounts of data. They know so much.
But they live in the digital world.
Exactly. And robots live in the messy physical world, needing real-time, continuous control. This paper shows a concrete method to bridge that gap effectively.
A way to tap into the VLM's brain without breaking the robot's body control, so to speak.
Yeah, it tackles that core conflict. leveraging the semantic richness of VLMs without sacrificing the speed and precision needed for physical action, and without destroying the VLM's knowledge in the process.
So knowledge insulation lets robots benefit from web-scale data, better language understanding, better generalization.
While still learning the fast, smooth movements needed for tasks. It avoids making that painful choice between being smart and being physically capable.
Do they mention any downsides or trade-offs?
The main one they note is a slight increase in computational costs during training, maybe around 20% compared to the simplest baselines, because you're doing both discrete and continuous predictions.
You said it converges faster overall than some other methods.
Right. It converges much faster than the purely diffusion-based methods like Sturo, so that initial extra cost per step seems to be more than offset by needing fewer steps overall. So maybe not a huge practical downside.
And they did say language following, while improved, still wasn't perfect.
Yes, that's an important point. They acknowledge it's better, but not flawless. They suggest limitations might stem from biases or gaps in the training data itself, which is a common challenge in ML.
Which kind of points to where things still need to go.
It definitely does. Even with clever techniques like insulation, getting these models to truly grasp the nuances of human language in every situation and reliably prioritize those instructions over maybe simpler visual patterns, that's still an active area of research.
This whole concept of insulating knowledge while adapting, it feels like it could be useful beyond just robots, couldn't it?
Oh, for sure. The general problem of how you fine-tune massive pre-trained models for new specific tasks without them forgetting their original capabilities, that's a huge challenge across many areas of AI. This work offers one potential strategy.
Well, that was a fascinating deep dive into knowledge insulation for these vision language action robot models. Really interesting to see these creative solutions emerging.
It really is. It shows how the field is tackling these fundamental challenges to make embodied AI more intelligent and useful.
And it leaves us with that interesting question you raised.
Yeah. If, even with insulation, perfect language understanding is elusive, what's the next big step? What else do we need to ensure these robots truly understand and follow our instructions reliably in the complex, sometimes ambiguous, real world?
Something for all of us to think about. A great place to wrap up. Thanks for joining us for this deep dive.
Always a pleasure.
Keep exploring, keep asking questions, and we'll see you next time.